Okay, today we are going now to study about the representation of functions as power series. So consider the series. So let's call it 1. You have already seen it before. 1 minus x is given by 1 plus x squared plus x cubed plus x power 4 x power n, which is just the summation from n0 to infinity of x power n, and this works when x is strictly less than, the absolute value of x is strictly less than 1. So we're going to use this series 1 to find other series to represent functions. So examples: 1. Express 1 over 1 minus x squared plus x squared as the sum of a power series and find the interval of convergence. So we are going to make use of question 1. So replacing x by minus x squared in equation 1, we have 1 over 1 plus x squared is the same as 1 over 1 minus, so which will be the same as, if you pick the same format as in 1, we'll have this summation. And then this can be written as n from 0 to infinity of negative 1 raised power n, x raised power 2n. And then if we were to write a few terms, we have minus x power 6 plus x power 8 minus several terms of the same pattern. So now, because this is a geometric sequence series, it converges when minus x squared is less than 1, i.e. x squared is less than 1, or the same way of saying, so therefore the interval of convergence is -1 to 1. Then example 2, find a power series representation for this function 1 over x plus 2. So solution. So we say that in order to put this function into the form of equation 1, we first factor out two in the denominator as so this is what we write. So we write 1 over x plus 2 is nothing but 1 over 2 into 1 plus x over 2. You see, when you open, you get the same thing here. So which is the same thing as 1 over 2 into 1 minus x over 2, which is still the same expression. So therefore now this one looks like the expression in the equation 1. So therefore it will be given by a half summation n from 0 to infinity of minus x over 2 power n, which will be given by summation n from 0 to infinity of now minus 1 raised power n over 2 raised power n plus 1 x power n. So therefore this series converges when minus x over 2 absolute value is less than 1, which implies absolute value of x must be less than 2. So the interval of convergence is minus 2 to 2. Example 3, find a power series representation of x power 3 over x plus 2. Now, by observation, you see that this function is the same as the function in example 2. The only difference is that we have multiplied it by x power 3. So we say since this function is just x power 3 times the function in example 2, all we need is to multiply the series in example 2 by x power 3, i.e. x power 3 over x plus 2 will be x power 3 times summation n from 0 to infinity of -1 power n over 2 raised power n plus 1 x power n, which is the same thing as summation n from 0 to infinity -1 power n over 2 power n plus 1 x raised power n plus 3. So you can write a few terms as a half x power 3 minus a quarter x power 4 plus 1 over 8 x power 5 minus 1 over 16 x power 6 plus etc. And then remember, another way of rewriting this is, so another way of writing summation n from 0 to infinity of -1 n over 2 power n plus 1 x power n plus 3 is just saying that x power 3 over x plus 2 is equals to summation n from 3 to infinity minus 1 raised power n minus 1 over 2 raised power n minus 2 x power n. Now this is how we are getting this. So we want now the power of the x variable to just be n. So remember, this n are just dummy variables. Dummy means that it can be taken by any variable. So you fix this one, n plus 3, say, is a value k. So it means that k will be given by n minus 3. Not really. N is equal to k minus 3. So which means that then at this point, n plus 1 will be k minus 3 plus 1 will be k minus 2. And then at this point, we have n, which is equals to k minus 3. So therefore now, this can be written as summation. Now remember, when n is 0, when you put n 0 here, k becomes 3. So therefore you start k from 3, -1, where there's n you put k minus 3, and then n plus 1 will give you k minus 2, and then n plus 3 gives you k. And remember, so this -1 raised power k minus 3 is just now changing the sign. So therefore, you can actually say, when you let now, k and n are just dummy variables, meaning that you can actually either decide to use k or n in your equation. So the same thing as saying, let k be n now, so n to be 3. Now this one, k minus 3, this simply means that now this you are always, this number will always be, when you pick k minus 3, the role of k minus 3, the same thing as saying just k minus 1. Because all these numbers, when this, assume this is 2, when you put here 2, you put here 2. 2 minus 1 is 1. 2 minus 3 is minus 1. All these are odd numbers. Or if you put here 3, put here 3. 3 minus 1 is 2. This will be minus 2. So k minus 3 and k minus 2, k minus 1, they have the same roles. when they are raised to a negative number. They think that now when this one is an odd number, you get a positive sign, a negative sign, and even number get a positive sign. So that's why we have this over 2 raised power n minus 2 x raised power n. And then now from that one, as in example 2, the interval of convergence is still negative 2 to 2. Please prove or show this. So then let's have another theorem here on how to differentiate and integrate a power series. Theorem, call it 2. If the power series has radius of convergence r greater than 0, then the function given by c0 plus c1 x minus a plus c2 x minus a square plus c3 x minus a cubed plus c4 x minus a power 4 is differentiable and therefore continuous on the interval and satisfy these two conditions. The derivative of that function f is c1 plus 2 x minus a plus 3, so 2c2 3c3 x minus a square plus several terms n cn x minus a raised power n minus 1. And then b, integral of f of x dx, the same as capital C plus small c naught x minus a plus c1 x minus a square over 2 plus c2 x minus a cubed over 3 plus which is the same as capital C plus summation n from 0 to infinity x minus a power n plus 1 small cn over n plus 1. So let's see the constant of integration. So the radii of convergence of the power series in A and B are both R. So you can integrate or differentiate the power series. So NB, point number 1, the equations A and B can be rewritten as, so let's call C, d dx of summation n0 to infinity cn into x minus a power n equals to summation n from 0 to infinity d dx of cn into x minus a power n. And then b can be written as integral summation from n equals to 0 to infinity cn into x minus a power n dx equals to summation n from 0 to infinity of integral cn x minus a power n dx. Note number 2, although the radius of convergence remains the same, when a power series is differentiated or integrated this does not mean that the interval of convergence remains the same. It may happen it might happen that the original series converge an endpoint, whereas the differentiated series diverges there. Note number 3. The idea of differentiating power series term by term is the basis for a powerful method for solving differential equations. So let's do some examples. One, express 1 over 1 minus x squared as a power series by differentiating equation 1. Remember, equation 1 is the series for 1 over 1 minus x. So solution. So differentiating both sides, of 1, we get, so remember the 1, for those who don't remember what we mean by 1, this was the series. This was the series that we are referring to as 1. So we'll have left-hand side will give us 1 over so this is what we're referring to as 1. 1 over 1 minus x squared equals to 1 plus 2x plus 3x squared plus 4x cubed. So which will be summation n from 1 to infinity of n x minus raised by n minus 1. So an equivalent answer is 1 over 1 minus x squared equals to summation n from 0 to infinity n plus 1 x raised for n. So always just play with these indices. It's a dummy variable, so then you say once we have this one, to shift the limits of summation, just say let k be n minus 1, so n will be k plus 1. So therefore you write this one as, so when n is 1, k becomes 0. So we have k from 0 to infinity, while there's n, you put k plus 1, and then where there's n minus 1, you put k, and then you just rewrite this new summation in terms of k, replacing k for n. You get this. Then you can say the radius of convergence the differentiated series is the same as the radius of the original series namely r equals to 1. So that's by the theorem that you have stated before, theorem 2. Next example 2 on the same. Find a power series representation for ln of 1 minus x and find its radius of convergence. So we'll still use 1. Solution. We notice that except for a factor of -1, the derivative function is 1 over 1 minus x, derivative of ln of 1 minus x, that's the value. So we integrate both sides of 1 so we have negative ln of 1 minus x equals to integral of 1 over 1 minus x dx, which will be c plus x squared over 2 plus x cubed over 3 plus other several terms. So which is the same as c plus summation n0 to infinity which is the same as c plus summation n from 1 to infinity of x power n over n for x less than 1. So therefore, to determine the value of c, we put x equals to 0 and obtain negative ln of 1 minus 0 equals to c, which means that c equals to 0, and ln of 1 minus x will be given by minus x over 2 minus x cubed over 3 x power 4 over 4, which is minus summation n from 1 to infinity of x power n over n for x less than 1. So therefore, the radius of convergence is the same as for the original series, which is r equals to 1. So notice that when I let x to be a half, then ln of 2 will be so when I let x to be a half, so I'll have, since ln of a half is the same as minus ln of 2, we see that ln of 2 is given by a half plus a quarter plus 1 over 8 plus 1 over 24 plus 1 over 64, which is the same as summation n from 1 to infinity of 1 over n to power n. So that is what we have for that given series. So next example, that should be example 3. Find a power series for f of x equals to tan inverse of x. So here solution would be, we observe that the derivative of that function is 1 over 1 plus x squared, and find the required series by integrating the power series for 1 over 1 plus x squared. We have already worked out this one. So tan inverse of x is the integral of 1 over 1 plus x squared dx, which will be the integral of 1 minus x squared plus x power 4 minus x power 6 plus dx, which will be c plus x minus x cubed over 3 plus x power 5 over 5 minus x power 7 over 7 plus several terms. Now to find the value of constant c, we put x for 0 and obtain tan inverse of 0 equals to 0, which means c equals to 0. So therefore now tan inverse of x will be x minus x cubed over 3 plus x power 5 over 5 minus x power 7 over 7 plus, which can be written as n from 0 to infinity negative 1 raised power n x raised power 2n plus 1 divided by 2n plus 1. And as usual, we say since the radius of convergence of the series 1 plus x squared is 1, then the radius of convergence of this series for tan inverse of x is also 1. So that is what we obtained. Then lastly, last example on representation of functions as power series. Evaluate integral 1 over 1 plus x power 7 dx as a power series. And then, so this is part A. Part B, use part A to approximate the integral from 0 to 0.5 of 1 over 1 plus x power 7 dx correct to within 10 raised to power minus 7. It's a nice problem. Solution. So the first step is to express the integrand (1 over 1 plus x power 7) as a sum of a power series. Now, as in example 1, we start by replacing x by minus x power 7. So this is not example 1, but equation 1, as in equation 1. So we have 1 over 1 plus x power 7 is the same as 1 over 1 minus x power 7, which is summation n from 0 to infinity of minus x power 7 power n. So which is the same thing as which is 1x power 7 plus x power 14 minus etc. So that's the series for 1 over 1 plus x power 7. Now integrate. Now integrate term by term. So we have integral 1 over 1 plus x power 7 dx equals to the integral summation n from 0 to infinity minus 1 power n x power 7n dx, so which will be c plus summation n from 0 to infinity minus 1 power n x power 7n plus 1 divided by 7n plus 1. This is just a normal way of integration using power. So which would be c plus x minus x power 8 over 8 plus x power 15 over 15 minus x power 22 x power 22 over 22 plus other terms. So this series converges for less than 1, that is for x less than 1. Part B, using the antiderivative given by the power series in part A, with c equals to 0, we have integral from 0 to 0.5 of 1 over 1 plus x power 7 dx equals to x minus x power 8 over 8 plus x power 15 or 15 minus x power 22 over 22, 0 to 0.5. So that will give us a half minus 1 over 8 times 2 power 8 plus 1 over 15 times 2 power 15 minus 1 over 22 times 2 power 22 plus minus 1 power n over 7n plus 1 times 2 raised power 7n plus 1 plus other several terms. And then from this one, you observe that this is an infinite series or just say this infinite series now this infinite series is the exact value of the definite integral but since it is an alternating series, we can approximate the sum We had already stated the theorem and when you're introducing the series. So if we stop, after the term with n equals to 3, the error is smaller than 1/29 times 2 raised to the power 29, 6.4 times 10 raised to the power -11, and we have integral from 0 to 0.5 of 1, or just dx over 1 plus x power 7 is a half plus 1/8 times 2 power 8 1/15 times 2 power 15 minus 1/22 times 22 2 power 22, which is roughly 0.4995137. So that's where I will stop. So do more practice on the same to be able to work out questions involving the expression of functions as power series. Have a good day.